This is a smooth horizontal disk, rotates about the vertical axis with a constant angular velocity omega naught. This is the constant angular velocity omega naught of the rotating disk. This disk is rotating about this axis, which is fixed, which is passes through the center of the disk. This is uniform disk, and it is fixed in our inertial frame of reference. At a distance a from its center, this is a distance a from its center, this is a point. A thin uniform rod is performing a uniform performing a small oscillation about this point. This point is a. This point is a. This point is fixed to the rotating disk, and here is a rod of some length. This is thin uniform rod. It is oscillating about this point of suspension, uh, passing through A. This has a rod or has a length small l. Suppose this has a length small l. AB is a thin uniform rod. This is a distance A. This is a distance A from the rotational axis. This is supposed to be an angular position theta at an instant t equal to t. We write the equation of motion. Actually, we write the equation of motion of this elementary part of the rod has a mass, differential mass dm, and because this rod is uniform, so if here is the distance from this is supposed to be x, so this differential length, elementary length of this rod, which is moving with a velocity v dash relative to the rotating disk. This is v dash perpendicular to the rod. This is dx. The position vector of this elementary rod is supposed to be r. This is vector r, and this is supposed to be the angle phi. We know that the equation of motion in any rotating frame of this elementary particle, rod particle, is equal to the mass into acceleration, of this rod. Actually, we apply Coriolis force for rotating frame. The Coriolis force is actually directed like this: mass of the disk, mass of the elementary, here this is the mass of dm, and omega naught cross of V dash. This is actually Coriolis force, or it is actually perpendicular to omega naught, and V dash omega naught is, you see here, is directed towards you, and V dash, so omega naught cross of V dash is directly uh, towards a point A along the rod. So minus of this is directed in this sense. So this is a Coriolis force as directed outward along the rod. This is minus of dm omega naught cross of V dash, and a centrifugal force, which is also a pseudo force known as pseudo force, omega naught cross of omega naught cross of r. Clearly this is also directed, this is the r, so this is actually radially outward, this is radially outward, this is a centrifugal force. Both forces are actually known as a pseudo force, not a true force. You see here the true force is net vector sum of the true forces acting on this is 0, but here is the tension force along the rod, and here is also the tension force. Both sides of the elementary rod is applied by the remaining part of the rod. Uh, so there is no information about this tension force. So actually apply the torque about A of these forces, which is a Coriolis force. This is actually this is actually a centrifugal force minus differential minus of omega naught cross of omega naught cross of r, and the tension force. The normal reaction force by the disc, rotating disc, is towards here, and so there is no torque about A of the tension forces of the either side, and the Coriolis forces about A. Only the torque about A, means the axis passing through A, is only due to the centrifugal force. And writing down here, we writing down the net torque in the sense of increasing theta, you may call an anti-clockwise. This is a moment of inertia of actually the elementary torque means differential torque on this element is nothing but only due to the centrifugal force. This is dm, the position r modulus r, and this is nothing but omega naught square of omega naught of r. We writing the torque of this force about this point. So r means the position of the action of the force. This force is actually has modulus x. So modulus of r and the cross of with f, which is also the modulus, like this, and the angle between the position r and the force is here because theta minus of phi. So sine of theta minus of phi. if we writing net torque on this rod, so must we integrate here. Suppose the only variable is x or phi. X and phi r is also variable, so we applying the chain rule for relating in one variable supposed to be in x. So we applying sine rule on this this triangle, thus a by sine of theta minus phi is equal to actually r sine of actually this angle, this is pi minus theta, so finally this is equal to theta, and also x by sine of phi. You see here r sine of from the sine of theta minus phi is equal to a sine of theta. So replacing this by a sine of theta, we got x, this is dm nothing but lambda dx, the linear mass density, square of omega naught, r sine phi is replaced a sine of theta. So if we obtain the net torque on the rod, means we integrating this along x equal to 0 to x equal to L. Within this integration, only x is variable, so taken outside, remaining lambda omega naught square and sine of theta, and only x dx, which is integrated x square by 2 and lambda nothing, lambda omega naught square sine of theta. If this is also taken outside, so finally the net torque, we obtain net torque acting on the rod acting on the rod in clockwise, that is in opposite of theta. So in anti-clockwise, this will be torque. Clearly a mass per unit length, suppose m is the capital M is the mass of the rod, omega naught square L square by 2 is sine of theta and minus sign. So if we apply the net torque on the rod in this sense, so net torque in anti-clockwise sense will be of the rod is equal to the moment of inertia of the rod about the point A and the angular acceleration in the sense of in anti-clockwise, which is equal to nothing but is minus of a m by m L omega naught square by 2 and sine of theta. You see here The rod is not oscillating in a simple harmonic manner, and but it is oscillating in simple harmonic manner in some special cases if theta is very small. So in this case, here is the moment of inertia of the rod about A is ml square by 3 d2 theta. This is the angular acceleration in anti-clockwise sense, minus of 2m to omega naught square, and it is theta if theta is very small. So this L1 is cancelled. So 3 by 2 with minus sign, and omega naught a omega naught square by L theta. Clearly this is actually uh, oscillation of the rod in a simple harmonic manner if theta is very small, of angular frequency omega under root of 3 by 2. Actually we have to find the angular frequency. Obviously the time period of oscillation is nothing but 2 pi by omega, means 2 L by 3a omega square naught. This is the time period of oscillation. It is very simple problem.